Okay, so now we've talked about how a magnetic field turns a moving charge. When we have a magnetic field, it changes the orientation of another permanent magnet, and also it changes the orientation of a moving charge. So if a moving charge and a permanent magnet both behave the same way in a magnetic field, it makes sense that a moving charge is also like a permanent magnet. So now we want to know what kind of magnetic field is generated by a moving charge or an electric current. So the reason that two magnets interact with each other is that they are both generating magnetic fields, and the magnetic field of one interacts with the magnetic field of the other. So that means that moving charges also must generate magnetic fields. Notice if the charged particle is not moving, then it does not generate a magnetic field, so the magnetic field does not affect the stationary charge, because that stationary charge does not generate a magnetic field. To start with, let's look at a simple example of moving charge and electric current. So here we are looking at how a current flows through a wire and how that generates a magnetic field. So you can see we have a wire coming out of a sheet of paper here, and if the current is flowing up, we can see that the magnetic field is perpendicular to the current and the wire. So notice how the magnetic field lines make a circle around the wire. The magnetic field generated by the wire is perpendicular to the wire. So if you move out some distance, the magnetic field will point perpendicular to the wire. If you are to the right of the wire and the current is out of the page, then the magnetic field will point up the page or down the page, I guess, depending on the direction of the current. If you put a circle of magnetic compasses around your wire, then the compasses will all tell you that north is a different direction, and so that it'll tell you that the magnetic force is perpendicular, and it will make kind of a circle around our wire. So this is another example of how a magnetic field is perpendicular to the direction of the current. One way of visualizing this is that if you are in a car and you are driving in a circle around the wire, the direction that your headlights are pointing is the direction of the magnetic field. Also notice that the closer you are to the wire, the larger the magnetic field, and the further away you are, the lower the magnetic field. To figure out the direction of the magnetic field, we use our second version of the right-hand rule. To find the direction of the magnetic field, you grab the wire with your right hand, and with the thumb pointing in the direction of the current. So as it is shown here, so the current is going up, and the thumb is pointing up, and so your four fingers are pointing in the direction of the magnetic field. So that means that the magnetic field is wrapping around the wire in the direction that your fingers are pointing. So if you're looking at it from above, the magnetic field would be counterclockwise and circle around the wire. Notice, again, this is very different from the electric field. If we have a point charge, then the electric field disperses with the surface area of a sphere. The electric field points either into or out of the charge. So as it disperses out of the surface area of the sphere, it will drop proportional to 4 pi r squared, and your field lines will point towards or away from the charge. On the other hand, with our wire, this will depend on the area of a cylinder, so that is 2 pi times r, and so that's going to be inversely proportional to the distance. And also, instead, it circles around the current. It doesn't enter or leave the current. Okay, so now we want to think about this quantitatively. Here we have Ampere's law, which tells us the strength of the magnetic field generated by a current. So the magnitude of the magnetic field generated by the current is mu naught. So this is a new constant. So this is 1.256 times 10 to the minus 6 newtons per ampere squared. So we multiply that times the current in amperes and divide by the radius and divide by 2 pi. So notice again, 2 pi r is the area of the cylinder, so the magnetic field is inversely proportional to the distance. The magnetic permeability is about the number of magnetic field lines generated by a certain amount of current. So the larger the current, the larger the magnetic field, and then the further away you are from the wire, the weaker the magnetic field. The thing is, finding the magnitude is usually the easy part. The tricky part is finding the direction of the magnetic field. So let's try a jump cut, and then we'll take a look at using the right-hand rule to find the direction of the magnetic field. Okay, so now we want to use our second version of the right-hand rule to figure out the direction of the current. So this can be a little bit difficult to visualize, so we'll do it using the document camera. So to start with, I've pulled out my little screwdriver here, so not the greatest demo, but basically this is showing you the direction that the current is flowing, right? So the tip of the screwdriver is the direction of the vector, and so that means we can kind of visualize it a little bit easier. So in our case here, we've got a wire, and it is oriented perpendicular to the screen, and the current is moving out. So that means our current here is moving directly out of the page, right? That corresponds to our dot. So the dot means the vector is coming out of the page. So that means our vector is coming out of the page. So that's what we've got. So now what we do is we take our right hand and we wrap our hand around it with the thumb pointing in the direction of the vector. So can you see my thumb here? Thumb's this way, and so it's basically going to wrap around. It's going to be a circle 360 degrees around our current. But you'll notice that means that, well, as we look down, that means it's going to be counterclockwise all the way around. So as we wrap our fingers around, we're going to see that the magnetic field at point B here, so this is below the wire, that is going to be pointing to the right. Right? So as we wrap our fingers around, it's going to be pointing to the right below. If we're looking to the left, it's going to be pointing down. If we're looking above, it's going to be pointing to the left. So essentially, our magnetic field here is wrapping around in a circle like that as we, that's the direction our four fingers point. So when we do that, that tells us that the magnetic field at this point here, points to the right. Okay, so that's one example here, and then next up we've got a case where the current is pointing to the left. So in this case, our vector is pointing to the left here, so again we do the same thing. We grab the vector with our right hand here, and so what happens when we reach point B? Well, here my fingers underneath the wire are pointing out of the page, right? So that means that if I grab this wire at point B, if I'm driving a car in a circle here, so to speak, so if I'm looping around my fingers, that means when I reach point B here, that means the headlights of the car would be pointing out of the page, and so that means that the magnetic field at this point below the wire is going to be pointing out of the page. So here, our correct answer is out. If we put B up here, then that means it would wrap around here, and so now my fingers would be pointing into the page, so at that point then the answer would be into the page. So yeah, so these can be a little bit tricky. This is another one of these examples where I think you have to practice them a few times, so we've got some examples for you to work out. All right, so I think this is it for the so-called Tuesday class, so good luck with the rest of the questions, and take care of yourselves.